Hi, my name is James Demma. I'm a graduate student at Virginia Tech in the Electrical and Computer Engineering Department. My project is laser harp, which I've done with the aid of the Amp Lab here at the ECU department at Virginia Tech. A little overview of my laser harp. I wanted to make an electric musical instrument. I want to use laser beams as the strings of the instrument, just as you would pluck the strings of a harp. To play my instrument, you break the beams of the lasers, and when you do so, it plays notes, and we'll get into the details of it as we go forward. The inspiration for this was my project from ECE 4534, which is Embedded System Design. Me and my group members made another musical instrument. This was done with an array of LEDs, IR LEDs and IR receivers. It was quite a bit more complicated, and not really because it needed to be, just because we had a lot to learn in that class. And so when we were done, I walked away with that with a lot of useful knowledge about digital systems. And I saw a video on YouTube that made me want to create this device. So I'm going to go away from this presentation for just a moment and show a little brief clip on YouTube. That's a Tetris game. I saw this video on YouTube, and the first thing I thought was, wow, that's really cool. And then the second thing I thought was, I could do that. I have all the knowledge to do that, and with just a little work and planning and engineering, I could put something like that together. So I had no idea how they constructed theirs, but I knew that I could construct one myself. My objectives: I wanted an instrument that was easy and fun to play. I wanted someone to be able to walk up to it and just start playing with having no knowledge of what it is or how it works, and just play music on it. I wanted to use easily available parts. Of course, they don't want anything complicated or hard to obtain, or if things broke, it would be hard to replace. Everything on here is free samples from Microchip, parts from Mauser, parts from eBay, and parts from the Amp Lab. I also wanted to be safe. This is a somewhat powerful laser that can do a lot of damage to your eyesight, so I didn't want to use anything too powerful. Everything here is also pretty inexpensive. The most expensive piece of the laser was about $100. Everything else is a lot cheaper. And I wanted it to be simple. I didn't want to have to spend a ton of time on this. I wanted it to be as simple as possible, and they're the best designs anyway. So here's a block diagram of my laser harp. It's actually not that complicated. I'm going to start with this in the middle. This is the microcontroller. It's a Microchip PIC 18F45J10. It's an 8-bit microcontroller. Has a lot of buses to connect things to. As you can see, everything going away from it is a bus. So it starts by sending some data over a SPI bus to a digital analog converter, which then gives me an analog signal that goes into an op amp. The signal range that the DAC gives me is not good enough, so I send it to an op amp that's arranged in a differential amplifier configuration. So that gives me -5, +5 range, which is what the scanner driver wants. And then that steps that up again to -15 to 15, which is what the mirror scanner wants. And so I send digital signals through this chain, and the scanner driver moves the mirror back and forth. So I set the position of the mirror, and then using a GPIO pin over here, I send a signal that's active high to the laser driver, which turns on the laser. At that point, I measure the light with the light sensor. I send an I2C message requesting data back, and then I can tell whether I have some light shining back from my device or not. If I do, I send a message over a UART interface to a MIDI synthesizer, which makes music. So, in a nutshell, I move the mirror, I blink the laser, I measure the light. If there's a note goes on or a note goes off, I tell the MIDI to take action, and we get music. So this is the laser harp. It's a little bit of a mess right now, there's wires everywhere. So that right here is the microcontroller. It's the biggest chip on there. This is the laser diode and the driver. The galvanometer scanner with the mirror attached along with its driver. There's the power components, the power supply, and 2 voltage regulators, one at 3.3 and one at 5. These 2 chips right here, it might look like one because of the wire blocking in the middle, but they're 2. It's the op amp and the digital analog converter. and my light sensor, which is a tiny, tiny little DFN6 chip there, mounted on a breakout board, and the MIDI synthesizer. And here is the supplementary equipment that I needed to get this done as well. It's a PID kit for programming the microcontroller, and a logic analyzer for monitoring all the digital activity on each of the bus interfaces. So here's my task diagram. It's really simple. There's only one thread. I initialize, I set up all the buses and the interfaces. Then I turn off the digital analog converter, send a position to it with the digital signal on the SPI bus, and then turn it back on. Actually, this should be right here. I turn off the laser, then turn on the DAC. Have to give it some time to wait for the mirror to move, because the signal's got to go through a couple stages, and then the galvanometer has to actually move the mirror physically, which takes some time too. And then once it's in place, I turn on the laser, I read sensor data, I compute any note changes, whether that particular note turned on or turned off, and then construct MIDI messages and send them off to the synthesizer. So this is what's going on with every loop inside of my system. Over here, this is the first event. This is where we send information to the DAC to tell it where to move the mirror to. And this is where I turn off the laser, wait for the mirror to move, then turn the laser back on. And then this is two I2C messages where I'm querying the light sensor for its data. The laser has a duty cycle of 57%, which is something I didn't take into account when I was designing it. I thought 150 milliwatt laser would be plenty powerful enough, but I'm dividing the laser by 8 since it's going 8 different beams, and on top of that, I'm only running it at 57%. So the individual laser beams are a lot less powerful than I anticipated them being. This loop runs at 694 megahertz, which equates to a maximum note latency of 1.44 milliseconds, which is plenty fast enough for you to not notice the difference from when you strike a note to when you hear it. A couple obstacles that some of them I saw, some of them not. Like I said, insufficient light deflection without use of reflective aid. The individual laser beams are not powerful enough to use your hands alone to reflect enough light to measure an appreciable difference in the light sensor. So I've been using some foil wrapped around my fingers, which has done the trick. My sensor started becoming inconsistent, and what became a major debugging problem because I had no idea why it was happening, and then eventually it just died completely. So that answers that. And also, which I didn't anticipate, but probably should have, that the sensor requires different calibration for each environment that you put it in. These lights are just shining up to the ceiling. The ceiling could be any distance from the top. It could be any real reflectivity. So I don't really have the baseline set until I take some averages and program that, and then measure changes against it. So this is my failing part that prevented me from giving you a full demo today. But this is recorded, so I hope in a week or two I'll be able to give you an actual playing of the instrument and go back and edit some of this video. And this is what I got from the amp lab. I got components when I needed them. It would be a real pain in the butt to have to order things like capacitors and voltage regulators whenever I needed one, have to wait a week to make any further progress when I got it ended. So I could go to Bob whenever I wanted and get these tiny parts. He just hand them out to me. It's been great. Voltage regulators, capacitors, connectors, jumper wires. I happen to have a MIDI synthesizer lying about, which is a big plus. And then equipment, PID kit, which I needed to program a microcontroller. And the biggest thing of all is the logic analyzer, without which I would not have got this project off the ground whatsoever. You can't see these digital signals with your eyes. You need a nice tool to tell what's happening on these interface lines. And some soldering. The sensor required some delicate soldering that I wasn't capable of, so Kevin Lee helped me with that, again with Amp Lab resources. And knowledge gain. I've done most of this before already, which is why I thought I could do it and then went ahead with it. But I did get some knowledge. I never used a SPI interface before, so that was new to me. Turned out to be very easy. And Bob tried to teach me a lesson last year, buy two of everything, because parts fail and things break. Didn't really stick the first time, but it's definitely going to from now on. And time for a partial, not complete demo. Okay, this is a bit of an incomplete demonstration. The sensor isn't working, so we can't actually play it yet. But, so this is showing my signals going through the pass to get my mirror working and the laser blinking correctly. So we have a single laser being fanned out to a bunch of lasers. So that part is being demonstrated. And we also have, I programmed a microcontroller to play different instruments, just a single note of different instruments to demonstrate that part working as well. So right now it's just going to play a note like every 3 seconds, different instruments. So that's everything but the sensor demonstrated, and here you can see the fan out of the 8. The idea was for this to be put on the floor when it's being played, so this would probably be about shoulder level, and I would strike a note by doing that, or by doing that, or by doing that. It's laser harp.